push that rock with some cement. We want to integrate this integrand right here. But to do that, I'm going to use my college algebra skills and complete the square. So I'm going to add a number here. Forget the 34 for a minute. Just kick it over here. I want a certain number here. So this is a perfect square trinomial. I want it to factor to two binomials that are the same, so I can write it as a binomial that's squared. And so in this case it'll be x minus something squared. And so to get 6, remember this would have to be, let's see, x minus 3 and x minus 3, because that would be 3x and 3x, which would give me 6x, and negative 3x and negative 3x. When I do the inner product, so it'll give me the negative 6x. And a negative 3 times negative 3 is positive 9. So I'm going to add a 9 here. Now, I can't just willy-nilly add a 9 to an expression that changes it by 9. So I'm not going to add a 9. I'm going to add a 0. So what I've done to my original quadratic is add a 0. Now that 0, I bust up. And I say, okay, that negative 9 I'm going to add to the 34 over here, and that's going to give me a 25 out here. And then this trinomial I factored to this. So I have x minus 3 squared. That gives me the x squared minus 6x plus 9. And then this 25 is just negative 9 plus 34 rewritten. And so I have rewritten this trinomial as a binomial plus a constant. Now I'm going to do one more trick. Well, maybe I should put it back into the integrand to see why. I'm going to run out of room quick. I wrote so big here, but we'll just go to a new sheet of paper. So I have rewritten this equivalently as this. If I expand this, combine like terms, I'll be back to here. So I haven't changed anything. Now, I'm looking at this and I see 1 over x squared plus a number. If I had 1 over x squared plus 1, it would be arctan. So I'm going to mess around and try to get that. I'm treating this as kind of like an x squared, just kind of ignoring it because it's linear. I know I can use Crawdad Hole rule. So I'm going to, this 25 though, I need to be a 1. So we'll factor it out. So we'll factor out from the denominator a 25. Oh, well, that gives me something weird here. There we go. Because 25 times this fraction, the 25's cancel, I'll be back to here. And then I get my plus 1. Well, okay, now this is complicated. I have this. But I can just make this part of that in there, right? I can rewrite that. Let me show you what I mean. I can change that to x minus 3 being squared over 5 squared. Correct? So 5 squared is the same as 25. Now I'm running out of room, so we'll definitely have to go to another sheet of paper. But I'm going to say, hey, this is being squared, this is being squared, so I can just write that fraction being squared. So that's what we'll do next. So we have the integrand of 1 over 25 times x minus 3 over 5 quantity squared. Because if I square this whole fraction, well, of course, I square the numerator and I square the denominator, and I'm back to the numerator squared, denominator squared. And don't forget your plus 1. Now we're really close to being able to use our Crawdad rule, whole rule integration. So I have 1 over 25 here, and I'm going to kick that out. So then I'm going to admit that this 5 is under both of those terms. And what I have is a linear function here. I have 1/5 x minus 3/5, and it's being squared plus 1 dx. And what I'm seeing in my mind's eye is 1 over x squared plus 1 dx, which the integral of this, the antiderivative of 1 over x squared plus 1, is arctan. And so, but this is, it's got a linear composition, but we know how to handle linear composition. So what I get is arctan of x, but our x is this linear composition, so 1/5 x minus 3/5. Put the reciprocal out front, so 5, but it's being multiplied by that 1 over 25, and then your plus c, and then maybe simplify. So I get 1/5 arctan of 1/5 x minus 3/5 plus c. And that's the antiderivative of the original integrand, which was 1 over x squared minus 6x plus, I think it was 34, with respect to x. So that's how you use completing the square to perform anti-differentiation. Math made simple. Simpson Math.